So we're going to take a look at the standard deviation of a frequency distribution. We're going to use the same drive-through service time data that we use through the measures of center lesson, in large part because one of the things we need in order to do this is the mean that we got from the frequency distribution. The idea being, of course, if we have the raw data, we use the raw mean, we find the mean of the raw data, and then we can find the standard deviation of the raw data. But if we're doing the grouped data, then we should probably use the mean that we got from the grouping. So we've got the classes as already defined, the frequencies as well, and as we did in the mean from a frequency distribution, we need the midpoint of the group. The idea, of course, is that we are using the midpoint as a representative value to say there are 10 data values in here, but without having the data set in front of us, we don't know what 10 values they are, so we're going to treat all of them as if they were the midpoint. And yes, some of the actual data values might be lower than the midpoint and some might be higher, so the midpoint kind of balances it out. Alright, so what we've got is the midpoint is our x value. We have the mean that we calculated in a prior video, and the frequencies, and those are the things we need to fill in these other three columns until we can ultimately get down to a total. So the nice thing is that the same way the midpoints follow the pattern of the class width, plus 38, plus 38, and so on, once we find the differences, the deviations, they're actually going to follow the exact same pattern. Because this is fixed, so when we do 101.5 minus 160, we get negative 58.5. And then if this is 38 bigger, that means it's also 38 closer to the mean. So if this is the distance from the mean, this one should be 38 closer. So we actually can do this a little faster rather than 177.5 minus that, 215.5 minus that. We can do the other route of just taking this value and add 38 to it, and add 38 and add 38 and so on. So let's fill in the rest of those. Now you can double check any of them, never a bad idea, but the next step, and this is where the calculator is going to come in particularly handy, is we're going to have to square these. Now, because they have decimal values, when we square them, we're going to have even more decimal places in the squared value. So, pull out a calculator. That's why we have them. So, we take each deviation and square it. Remember, the point of squaring the deviation is to remove the negative sign, because we don't want the negatives here to balance out with the positives later on in such a way that would cause the whole sum to come out to 0. We want to maintain that, but the idea is, of course, that something that's farther away from the mean will contribute a larger number to the sum than something that is closer to the mean. So we can see that here. Something that is almost 60 away from the mean is weighing in very heavily, whereas something that's only 20 away from the mean, not as much. And of course, even though this number is on the other side, it is almost the same distance, just on the other side of the mean, 20 below it and almost 20 above it, so they have a comparable weight. Whereas, again, these two, the 58.5 and the 55.5, are almost the same distance on opposite sides, and they have almost the same amount of influence, of weight, in the the sum of these square deviations. Now, of course, we don't end there, because it looks like this last one has a tremendous amount of weight compared to the others. In fact, more than all of the others combined. Well, that is then balanced out by the lower frequency. See, this is pretty close. Both of these actually are pretty close to the mean on one side of it or the other. So they don't seem to have a very big influence here as far as the square deviation, but they have some of the highest weights as far as how many values are in here. See, now, again, we're treating this as the representative value. This is its deviation, and that's the square deviation, but we need to account for the fact now that there are 20 such values in there. So that's where the frequencies are going to come in. We're now going to take the square deviations and multiply by the frequency. Now, some of these, like multiplying by 10, are easy. Others, you might want to use a calculator for. Again, nothing wrong with that. I'm using it. Be very careful here. It is with all these numbers all over the place. It's very easy to pull the wrong numbers for multiplication. So just make sure that you're taking the square deviation times the frequency, and just double check that on your calculator. So one of the things we can see here is that while this might not have been a huge number, it actually does end up, because of the sheer frequency of that class, having a greater influence than we might otherwise have thought. Whereas this down here isn't nearly so massive anymore. I mean, it far outclassed everything else, but now it's actually got pretty much the same amount of effect in the standard deviation as the first class, which is closer, but has more of them. Further away, but fewer. So, we now are ready to add all of these up. Now, remember, this value that we get here is not going to be the standard deviation. It's only going to be the numerator of the standard deviation fraction. So it's only going to be the top of it. Again, calculator. Now, it does get annoying having to type all of these numbers in over and over again. There are ways to use technology to do this a little faster, even without having access to the individual data values. Again, just double check as you're going, make sure that you have typed in all the values correctly so that you get the right result. 121,902.5. Now, yeah, that's a large number, which should not be terribly surprising, considering that we're looking at some fairly large numbers, and there are 50 of them, and this is adding up the squared distances for 50 numbers. Yeesh. It's going to be a big number. Now, we're not done with it yet. Again, that's just the numerator of the standard deviation fraction. So remember that the n is the sample size. So in the denominator here, we're going to have to subtract 1. So our standard deviation then is the square root of 121,902.5 over 50 minus 1, or 49, if you will. And again, we can use a calculator. You're going to have to because of the square root, if nothing else. So again, just be careful how you type it in. If you need to, do it one bit at a time so that you don't make any mistakes and accidentally have things happen out of order. But what we come out with here is 49.877, etc. So again, going by the rounding rule, if the data is measured to 1 decimal place, we will round the standard deviation to 2 decimal places, or what have you, always 1 more decimal place. So the original data had whole numbers, no decimal places, so we'll round it to 1 decimal place. And that's actually not that far off from the standard deviation that we find when we do it individually. So like the mean, it's not perfect, but it is pretty comparable. But that's really all there is to it. And if you are comfortable finding the mean from a frequency distribution, this is, while slightly more annoying in the number of digits in each value, it's really not all that bad. It's the same basic things. We just add in that extra step of having to multiply by the frequency at some point. In this case, we're multiplying the square deviations by the frequency. And of course, don't forget to take that value and do the rest of the standard deviation formula with it. Now, there are ways to do this using the calculator or using Microsoft Excel. So I'm going to have some videos of that to help kind of make this a little bit more manageable, because some of these numbers are very big, and it does get annoying to have to continuously calculate it, write it, and then later on do another calculation, which means you have to retype it, and then add all of them up, which means you need to type it again. It gets annoying having to type it over and over again. So it would be kind of nice if maybe we could just do one quick string and then have all of these like stored in one spot that we can add together. So there is definitely ways in technology to do that, which is very handy. Even if you don't have the raw data for the technology, it still makes these calculations faster. But again, the procedure is very, very similar to that of the mean of a frequency distribution, just got a couple more steps in it. And the numbers, unfortunately, tend to be a little bit bigger and a little uglier.